Hey, what's up, chem peeps? What in the heck are we gonna do in this video? In this vid, we're gonna use thermochemical equations to calculate energy changes that occur in phase changes and classify those changes as exothermic or endothermic. As always, breaking it down, we are going to 1. Write thermochemical equations for phase changes. 2. Explain how the average kinetic energy of a substance relates to the phase of that substance. 3. Label and explain parts of a heating or cooling curve. 4. Define and calculate molar heat of fusion or molar heat of vaporization. Finally, 5. Calculate the total heat absorbed or released during a phase change. Alright, so there's a lot there. First thing we're going to do is recognize that in addition to chemical reactions, heat energy must be absorbed or released to transition from one state of matter to another. So as you take a look at your screen and at the table that's in your notes, recognize that if we melt, condense, vaporize, sublime, or freeze, all of those processes require the absorption or release of heat. Now, many times we're going to depict those phase changes as it relates to energy absorbed or released by drawing what is called a heating or cooling curve. And this is just a graph of the temperature of the system versus the amount of heat added or removed. If it's added, we call it a heating curve. If it's removed, we call it a cooling curve. Take a quick look at your screen to give you an example of what a heating curve is going to look like. This particular heating curve represents the heating curve for water. Think about what is going on at the molecular level as we move throughout this heating curve, and think about the average kinetic energy that those molecules have. Initially, at temperatures less than 0 degrees Celsius, water is a solid, relatively little average kinetic energy of those particles. As we heat that solid up, it's not going to begin to melt until we hit the melting point of water at 0 degrees Celsius. Here we've got a mixture of the two phases, solid and liquid phase, greater amount of average kinetic energy. Notice that the temperature of the system stays at 0 degrees Celsius until all of the solid melts. At that point, we have all liquid, and as we continue to add heat, we just get hotter and hotter liquid water until we reach 100 degrees Celsius, or water's boiling point. At that point, we once again have a mixture of two phases, this time the liquid phase and the gas phase. However, once again, we don't have a temperature change until all of the liquid has evaporated and is turned into the gas phase. Then we just get hotter and hotter gas. Average kinetic energy going crazy. Now, a big part of what we're going to do here is analyze how much heat was absorbed or released as those phase changes occur. And we can use the heating curve or cooling curve to help us out. First thing you want to do is recognize that when you're working on a sloping segment of the heating curve or cooling curve, you will simply use the formula Q equals MC delta T to solve for the amount of heat absorbed or released for that part of the curve. Now, a couple things to keep in mind about those sloping sections. Recognize that the angle of that sloping portion is related to the specific heat of the phase of that substance. The steeper that slope is, the lower the specific heat, because it requires less energy to increase the temperature. The more gentle that slope is, the higher the specific heat, as it will take more energy to increase 1 gram of that material 1 degree Celsius. Take a look once again at this example heating curve of water. You're going to use MC delta T anytime you're working at one of the sloping sections. But if you're on a plateau section, the calculation is a little bit different. There is no delta T, there is no change in temperature. So when you're working on a plateau section, you're going to use what's called the molar heat of fusion, when we're talking about melting or solidification, or the molar heat of vaporization, when we're talking about vaporization or condensation. In other words, we're talking about the melting point or boiling point of that substance. How much heat do we have to add to completely melt or get all of the solid to turn into the liquid? Or how much heat do we have to add to completely evaporate or get all of the liquid into the gas? And again, that's simply known as the molar heat of fusion or the molar heat of vaporization. Now, a few things to keep in mind about the plateau regions. There is no delta T. The substance remains at a constant temperature. Again, that's our melting point or boiling point. The molar heat of vaporization or the molar heat of fusion are unique for each particular substance and are generally measured in kilojoules per mole or joules per gram. So this will either be provided to you in the problem, or you'd have to look at a reference. The final thing to keep in mind about these plateau sections is to recognize the length of the plateau is directly related to the amount of heat required to make the phase change. If there's a longer plateau region, that means it requires more heat in order to complete that phase change. All right, and then finally, recognize that many times you're going to be asked to calculate the amount of heat required to go through multiple phase changes. So maybe from solid to gas or from gas down to solid. All you have to do is sum together the heat energy values from each of the segments. So take a look at your notes. You're provided with an example in which we want to think about how much total energy does it take to completely get 1 mole of solid ice at negative 25 degrees Celsius up to 125 degrees Celsius in the vapor phase. All you need to do is perform a calculation for each of the segments and then sum them together. For our first segment, our solid ice at negative 25 degrees Celsius up to 0, a sloping segment. We're going to use MC delta T. Plug in the values and solve. Our Q value for this segment is 0.941 kilojoules of heat. That's how much heat it took to take our solid from negative 25 degrees Celsius to a solid at 0 degrees Celsius. Next, we've hit the melting point. So here we've got a plateau region and we'll use the molar heat of fusion. We're simply going to multiply our number of moles by that molar heat of fusion, which in this case for water is 6.02 kilojoules per mole. So the amount of heat required to completely melt our solid into a liquid, 6.02 kilojoules. Next, we need to heat up that liquid from 0 to 100 degrees Celsius. Sloping segment, MCAT. Simply plug in the mass, specific heat, and temperature change for that segment of our curve, and we calculate 7.52 kilojoules to completely heat up our liquid water from 0 Celsius to 100 Celsius. Total amount of heat energy required for this segment of our curve, 7.52 kilojoules. Next, we gotta take all of that liquid water and get it to evaporate or turn into the vapor phase. Once again, in this phase change or plateau region, there is no temperature change. In this case, we're going to use the molar heat of vaporization, which is given to us as 40.7 kilojoules per mole. Boom. And then finally, to heat up that vapor from 100 degrees Celsius to 125 degrees Celsius, we're once again on a sloping segment. We aren't changing phases, we're just going from a gas at one temperature to a gas at a hotter temperature. So we'll once again use MCAT. Plug in those values, we get the heat required to do that to be 0.904 kilojoules. And then finally, if you wanted to know the total amount of heat energy that was required to go from that solid ice, that solid water at negative 25 degrees Celsius to water vapor at 125 degrees Celsius, all you gotta do is add together the heat required for each of those individual steps. Total amount of heat for this process to occur, 56.1 kilojoules. All right, and that does it for this video. Have a fantastic day.